I open this public meeting of the College of Deans of Vrije Universiteit Amsterdam for a PhD ceremony of the Faculty of Science by affirming that from our Christian origins to the present, we practice science with a sense of wonder and inspired by fundamental values. Prior to his examination, I invite the candidate to give a short presentation on the work in his dissertation. The floor is yours.
Let me start with introducing a bit the cover art of my thesis. When we look at nature, we can see there's a plethora of animals that are very well adapted to their specific environment. So the idea then arises that if natural evolution can work for so many animals in the wild, why can't artificial evolution work for robots in the wild? And so this is the idea behind evolutionary robotics. Imagine you have a population of robots that you let loose in nature, and all of a sudden you see two robots that are really good. So we want to select them for parenthood, which means that we can take their DNA, some ones and zeros in our computer, and combine them in such a way that a new robot exists. And then hopefully this new robot has some properties of either of its parents. So for example, you can see here that the right arm of the blue robot and the legs of the green robot is present in the baby. So this is quite straightforward for the morphology, but unfortunately, this is not as easy for the brain. And this is not so unsurprising, right? When we look at nature and you compare a kangaroo with an ostrich, both are really good runners with two legs. But when you would combine their walking behavior or their brain, it would actually not work. That's why we try to introduce an infancy stage. This stage means that we give the brain some additional time to adapt to its new body through some learning iterations. And so this learning iterations or this learning period was the focus of my PhD. How can we design learning algorithms that help the evolutionary process in the end? Because the evolutionary process brings some extra complications with it. First of all, we looked into the fact that we actually don't really know what type of robots we are dealing with, so we cannot control them. This is because evolution can produce any type of machine. So how do we deal with that as humans? Let's say we want to control this strange machine with two wheels here at the bottom. Then we can send some actions to our legs, and the legs will then push on the pedals. And subsequently, when we move forward, we see some light on the retina shifting. All this information is then parsed inside of our brain, and somehow there's an internal model of what this machine can do. And therefore, we then know how to predict what will happen next when we steer to the left or when we steer to the right. And so this action and prediction models, they make it possible for us to control this strange machine, the bike, right? And now a question that you can ask yourself, are we born with this model of a bike in our head? Or is this something that we learn throughout our lives? To disbelief of my fellow Dutch people, this is actually something that we are not born with. So we don't have a model of a bike in our brain. And this is something that we learn through our lifetime. So similar for our robots then, we should also try to learn a model because we don't really know what will happen during evolution. And so our models should also be able to adapt during the lifetime of the robot. We used for this some neural networks that are able to continuously adapt and slowly then understand what the robot looks like and how we can control it. And so this works really well for learning control. And you can also use this type of thing to continuously adapt for new environments. So let's say we take a robot from simulation and we want to put it on the real world. Then all of a sudden, there might be some sim to real gap or reality gap, and we can still adapt to this new environment. So now that we know how to control our robot, we actually want to make it perform some tasks. So for example, we want to say, please walk from point A to point B. For this, we need some additional skills. For example, you need to be able to walk, you need to be able to look around and rotate, which means that when you think about it, that you do this in an evolving population, then all of a sudden you have many skills to learn with every robot that you get. And so we have to think very smartly about time and efficiency. So in nature, we can see that we are actually quite efficient. After a couple of minutes, some animals are able to walk and move around. And even for us humans, that take 1.5 years to learn how to walk. Straight after birth, they already have these coordinated walking patterns that are very similar to what adults do when they are walking. And so how we do this is that inside of our spinal cord, there are groups of neurons that are wired in such a way that they turn each other on and off reciprocally. And the nice thing about this is that we can take these neurons and we combine them in a bunch and have a big network. And all of a sudden, your robot then starts to move. So the amazing thing is that this is without any form of learning. So what you see here is just us imitating this network, and we throw it on the robot and it immediately starts to move. Then you can say that this movement seems quite chaotic, but when you look very closely, you can actually take certain patterns that are very useful for the skills that you want. So for example, you want to move forward or you want to rotate. You can then take these patterns in a way that you couple them one by one, and all of a sudden your robot just starts to behave, be able to perform tasks that we assign it up. So after 15 minutes of doing this, we were already able to make our robots move from point A to point B, all without learning. So we made a lot of progress now. We learned how to understand what type of robot we are dealing with. We can control it. And now we can also perform certain tasks with it based on the skills that we acquired during its life. But this is still quite focused on the individual itself. And this neglects the parts that we are actually dealing with the robot population. So at the end of my PhD, I got more interested in how can we work together maybe as a population itself, which is something that you see in nature all the time, right? So for example, you see here fish that try to aggregate in the shadow because it's more cool in the aquarium. And then when you drop one fish in the aquarium, it's not able to do this, so it gets lost. But by working together, they can feel through the water how other fish moves, which makes it easier for them to aggregate in the shadow and move as a group correctly. And very inspired by this phenomenon, we were thinking of maybe trying to learn some robots to work together in a similar type of task. So I really tried to convince my supervisors to buy a big aquarium, but unfortunately they were hesitant to do that. But in the end, we got these cute little ground robots here, and we tasked them to find the light source, the one that you see in the center of the arena. And so when you learn long enough, all of a sudden you can see that our robots are able to perform this task successfully, mostly because they are able to collaborate, right? So what is nice to see here is that you can actually see a bit the behavior that you saw with the fish back, where they encircle each other and then start interacting with each other up until the point that they find the center of the light. And so these results are quite recent, but I think it already provides a very nice insight in what can be down the line for the future. We talked about these robots that evolve and then maybe specialize for their different niches in a big ecosystem. But then if you want to, or if you let them work together, it really starts to look a bit more like this original picture that I drew, right? Of artificial evolution for robots in the wild, what exactly the end goal of evolutionary robotics is. So to put it all together now, we started with zooming in on this evolutionary robotics, and we looked at this infancy stage. And we saw then in the end that throughout the life of a robot, we were able to create a very self-reliant robot that could do tasks in the world, and then in the end work together in a big robot population. So I think that's for me, that's the end of all it. And I want to close with this last.